All right, everybody. I've made the executive decision not to use the projector because for the most part these problems can be written on the board. We will have covered 6.5. We will have covered 6.5 by the time you watch this video. But since you have not seen it, if you didn't take notes today, I'm going to introduce first the law of cosines. You might see this formula written with different letters depending upon the triangle that's drawn to demonstrate it. But I think the best way to think about it is that when we have an included angle between two sides, then that side, the side opposite the included angle squared, is equal to the sum of the squares of the two sides that enclose the angle minus 2bc, which are the two sides enclosing the angle, times the cosine of A. I suppose I'll answer this phone. Hello? Well, this is Andrew Fucarino. I'm recording a video in the room right now. If you're looking for Dr. Glenn, he's not here. No, I do not. He's in the chemistry room, which is room 305, I believe. Okay, that's the lab room. He's a couple classes down. Yep, by the tables. All right. Sorry about that, everybody. So my point is that really you just have to look at it as when I have an angle and I'm going to use the law of cosines, then the side that's going to be squared by itself in this formula is the side opposite, and the two sides that go together are the sides that enclose that angle. So it's not about A, B, or C in the triangle. Those are arbitrary letters. So let's just get into the first problem. Number 14 gives us, it does not give us a picture, A equals 10, B equals 12, and C equals 16. I'm going to draw the same triangle every time. A equals 10, A, B, and C. And these are angles A, B, and C, which we use capitals for. So lowercase a, the side length would be 10. I always write out a column, a pair of columns. For my sides and my angles. A would be 10, B would be 12 here across from B, and C would be 16. So I have to solve for the angles, and I'm going to start by writing out the law of cosines, but with the angle A as the included angle. So 10 squared, which is the side opposite, that is A squared, is equal to 16 squared plus 12 squared minus 2 times 16 times 12 times the cosine of A. Like I said, I just match this side up with this angle, and as long as I have the lengths of the other two sides, then I have an equation that I can solve or isolate A in. And I'll skip the work for that just a little bit to get cosine by itself. Well, if I add this term on the right to the left side and I subtract the 10 squared, there's fewer negatives. So getting cosine by itself. We use this to solve for the angle. So lastly, I would use the inverse cosine to solve for a. A equals the inverse cosine of 16 squared plus 12 squared minus 10 squared over 2 times 16 times 12. Can we still see that, Rami?
Yep.
Okay. And I solve for a. Plug that into my calculator, and I get 38.62 degrees. I'll mention this in class later today, but cosine does not have two positive solutions for numbers between 0 and 1. There is not the possibility of some ambiguity or an extra triangle when you use the law of cosines. As long as you use the law of cosines in a situation like this, where there is no ambiguity, that would be side-side angle. Since I have side, 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 and that would be enough to prove two triangles congruent, these three sides being given defines only one triangle, and that's mainly why I start with the law of cosines. What I did, and I might leave that work to you, is I did the same work to solve for angle B. No, I'll show you. 12 squared equals 16 squared plus 10 squared minus 2 times 16 times 10 times the cosine of B. You see what I mean? If I want to solve for B, I'm going to plug in the side lengths with the side opposite from B by itself, the sides that enclose angle B together at the beginning, and these are the same letters always in that formula. This I will skip the steps for, and I'll say that B is the inverse cosine of 16 squared plus 10 squared minus 12 squared over 2 times 16 times 10. That look good, Rami? No, I mean the math.
Oh.
So yeah.
Yeah.
All right. I think so too. And this gives me 92.87. I feel it is easier than the law of sines, especially to set up, knowing that you have all three sides on a triangle. That thought process of writing the side opposite from the angle you're solving for by itself and plugging into this formula that is the same every time. But again, keep in mind, this is not about angle A or side A. This is about a side and the angle opposite that side combined with the two sides which surround that angle. I could also write, just for example to make sure we understand, c squared is equal to a squared plus b squared minus 2ab, which is actually usually how the formula is written. But I think it's really important to know that that's not always necessary. A, B, and C are just arbitrary letters that we applied to the sides of the triangle. Okay, what would you do next? Don't do the law of cosines again. That would take too long. We have two angles. We can add them together and subtract them from 180 degrees because the three angles must add up to 180 degrees, and we can get the third angle. And that's it for that. Okay? So you definitely use the law of cosines in the side, side, side case. Didn't need to erase the triangle. I'm going to draw the same one every time. Okay. 15. In 15, I'll read that there, we are given B, again, I got to recycle more. B is 125, C is 162. And and angle B is 40 degrees. Just helps you to see where everything is going to be when you have a triangle to draw on. All right. The other reason that we should write the sides on an actual triangle is we can identify when we have a potential ambiguous case. This is side-side angle. And so, although I could maybe use the law of cosines to solve for something, we have to approach this the same way we have in the previous chapter, the previous topic. So that's with the law of sines. And since I have the two relevant the angle inside for angle B, I'm looking at angle C. So sine of C over 162, sine of 40 over 125. So sine of C is 162, sine of 40 divided by 125. It's totally fine, like I did during class, to check whether that number on the right side is greater than 1. If you don't, and you directly solve and you get C by itself and you say C is inverse sine, you'll find out that it doesn't work, or it does work, because your calculator will give you a domain error if the number on the right side of that equation is greater than 1. Sine is not greater than 1 for any angle. But this time around it does work out, and we get angle C to be 56.41 the first time around. But I've said the word ambiguous a few times now, and the reason it's ambiguous is because, like I've said, this equation right here has more than one solution. On the right side, I have a positive number, meaning that there are two possible angles, one in the first and one in the second quadrant, which would represent a solution to this equation. And that doesn't mean that those two angles necessarily exist in this triangle. We have to check, but because I use the law of sines, it is possible to be ambiguous. So what I do, as we did many times the other day, is we subtract this angle C that we solved for with the calculator from 180 degrees, and that would be the beginning of our third triangle. I'll write it over, our second triangle. I'll write it over here. Angle B is still 40. Angle C, I have that, could be perhaps 123.59 degrees. Again, I got that by subtracting 180 minus the angle C. I did that because sine of C equals a positive number has two possible solutions. What do I have to do next? I have to add these two angles together to make sure that they do not represent more than 180 degrees, which wouldn't leave room for the first angle or the third angle in this situation. Those two do not add up to 180 degrees or more, and so that would mean that I can find the third angle. And if you look, 16.41. I do that before I solve for the sides of either triangle, but we just got to make sure we keep things separate. The third angle in this triangle is 83.59. And how can we solve for A? Well, I use law of sines because I do think sometimes that's a little bit quicker. So I could set that up, still using the sine of 40 over 125. Is equal to, well, I'll write it as sine of sine of A, but we know A already. I just don't want to teach you to round in the middle of the problem. Sine of A over A. But we know this number, right? And so cross multiplying A sine of 40 equals 125 sine of A. And side A is 125 sine of A over sine of 40. Plugging in the same angle A that we solved for by subtracting B and C from 180, which you can do in your calculator without retyping this. What I did when I did it, we get 193.25. The nice thing about the way that I wrote that is that in this triangle over here, A is still equal to 125 sine of A over sine of 40. Except that A is 16.41. And I'll use that number when I plug into my calculator here for A. And when I do that, I get a different value for the length, 54.95. And then B and C are still the same, they were given. Yes, you may use the law of sines entirely in this law of cosines homework. Part of using the law of cosines properly is understanding when it applies and when it does not apply. Okay. The next one was good, so I'd like to do that. I probably won't have time to get through the entire homework. That was a bold claim that I was going to try to do that, and I am trying to do that. But we will get through as much as we can, and I'll make sure that I get a word problem in. We could talk about bearing, which we will do today. Don't erase the triangle. All right. For 16. We are given, what do I want to write it? Angle C is 52 degrees. Side C is 50. Let's see if I can get it better. Side A is 65. Okay. So that would be 50 over here, 52 over here, and 65 over here. Angle, side angle. Again, it is ambiguous potentially. But I would still use the law of sines. Sine of 52 over 50 is equal to sine of A over 65. Now, if you type that in right away, you're going to get domain error. I got domain error when I typed it in all together. But to double check, what I did was calculate 65 sine of 52 over 50, what was inside of the inverse sine, and I found that that was just a little bit over 1. And anytime the argument of the inverse function is greater than 1, then it is not defined. And so that means, after all that work, no such triangle exists. No such triangle exists. Let's see, anything else good in there? Not too much that we didn't see, which is good. I will do number 20, and then I'd like to try to get to one word problem, at least. In 20, they changed the angle location on me. I was close. In 20, they put C up top and B, and they say we have 40 degrees, we have X, and we have 4 and 11. You don't want to use the law of cosines in a case where the included angle, and especially the only angle that you have, is is touching one of the two sides that you do not know. So that's because that side in question shows up in two different places in the equation. So if I didn't know this side length right here, it would be here and there. And that's really here and there. And that's not really what we're trying to do because we can't solve that as easily just by isolating. But this is a perfect situation to solve for a side using the law of cosines because the opposite side, and I'll write it as an x. I think you really got to get over the whole A, B, and C representing particular sides of a triangle. They are not special. Most of these triangles are scalene. They're all just different side lengths. X squared is equal to 4 squared plus 11 squared, the two sides that enclose the included angle, minus 2 times 4 times 11 times the cosine of the included angle. Included means it's in between. Maybe you didn't know that when I've been saying it. The included angle, not just say it's included in the problem. Right? And so because I know everything on the right side, I could isolate very easily. I just take the square root. I won't leave off the plus minus, but we only have positive side lengths. And so that's true only arithmetically. 4 squared plus 11 squared minus 2 times 4 times 11 times the cosine of 40 degrees. Admittedly, I haven't done that in advance. So if we're curious, I'm going to need to tell you. Give me a moment. You know, in some parts of the world, there are calculator competitions.
Really?
Mm-hmm.
Like how fast you can type it?
Yeah, they'll give you a long list of numbers, and you have to add, subtract, sometimes multiply them more quickly than anyone else. I watched a documentary about it once. Very interesting.
What kind of prizes do they win?
I'm not sure. The sound in the room is unbearable, just the clicking of the keys. Well, that looks good. 8.34. Does that sound reasonable? It does sound reasonable. 8.34. Cool. Now we got it. Did they say solve the triangle? Find the indicated side x? Well, that's nice. I'll leave these to B. I don't need to know. I would have used, just so you know though, I would have used the law of sines. And we would not need to worry about an ambiguous case and not even need to subtract from 180 degrees from the answer that we got for angle C or angle B, because the original problem statement was side angle side. That's firstly why I started with the law of cosines. And secondly, that only defines one triangle. So I would find C and B relatively easily from the law of sines, and I would not need to check for a second triangle because there is only one triangle that can exist with those dimensions. All right. Yeah, I think in the interest of time, it's only 9:35. Not so bad. We can move to some word problems. What did we assign? 42, 44, 49. I think we ought to start with 42. I would love for you all to try this on your own, but I think since I will not be here, it is only fair that I give you something that you can check your answers against. What about this blue, huh? Is that visible?
Yeah.
Okay, so this has to do with bearing. And bearing is a way of indicating a direction, but at least on the diagram, they've drawn the angles in the appropriate locations. But it actually really defines what something like north 50 degrees east means. I mean, if you think about it, it's a great way of telling someone which direction to go. Point north, but then turn 50 degrees towards the east. Never eat soggy waffles, you know? And then, but there's a diagram anyways. Here's a 70-degree angle. And that was defined as south 70 degrees east. Point south and then turn 70 degrees towards the east. Right? So I can find what we should be thinking of is the side between them. These are two ships, two boats that are traveling in opposite directions, and in the end we're asked how far apart the boats are in 1 hour. So that would be that side length. So this is the triangle that I'm trying to solve, and I really want an angle inside of that triangle. I want the internal angle here. So these two angles add to 120, and this internal angle here would be together with that one straight line. So that means that the internal angle here is 60 degrees. Does that sound right, Rami? Yeah, 60. We're cool. Right? But then we need side lengths. Again, this is actually another classic case of the law of cosines where we have two sides that include an angle. But the way they've given it is maybe a little confusing if you haven't done a lot of physics. One travels at 30 miles per hour. How far are they after 1 hour? Well, after 1 hour, at 30 miles an hour, the first boat will have gone 30 miles. Should have made it 2 hours, make it interesting. After 1 hour, the boat that is going 26 miles an hour has gone 26 miles. And again, just like the problem that we just did, you have two sides here. Maybe I'll draw it separately. And an included angle. This could be our x, and aside from the numbers being different, this is not any different from the last problem that we just did. Wouldn't you agree?
Yeah.
Cool. Solve for that, but you know I can't do it all for you. You're just plugging in. Like I said, it's just like the previous problem that we just did. All right, can I draw Egg Island? Mm-hmm. 70 degrees. Degrees. And they told us the distance is 50 and 30.